Alright, so it is a Saturday night, so there might be some background noise, like very faint, but probably won't be a big deal. So, anyways, we want to prove that there's a continuous function on this set which is unbounded. But this requires that the set A is not closed. Alright, so since A is not closed, a complement is not open. So, a complement is not equal to the interior of a complement. Because we know that open sets are sets which contain their interior. Do we know that? Well, if we think about it, okay, so if we've talked already, I believe, in this chapter about if you have an open set, then any point in the set is in the interior. And then certainly, let's see, so if you have a set such that every point is in the interior, then you can just take the union of all of those. Like for each point, you take a neighborhood, and then you take the union of all those, and then that's a. Oh, well, I guess that uses the fact that arbitrary unions of open sets are open, which is not how we define an open set. I forget how we define open sets, but whatever the definition in this textbook is, it is true that open sets, a set being open is equivalent to the set being precisely its interior. Okay, so A complement is not open, so A complement is not its interior. So there exists some point X in AC such that, okay, X is not in the interior of A complement. Because certainly the interior of A complement will be a subset of A complement. So the fact that they are not equal means that there's something in A complement which is not in the interior. Right, because basically what's going to happen here is that this point X, which is not in the interior, it's basically going to be on the boundary. It's going to be on the boundary of a complement. Yeah, so this will work. So just reminding myself how this proof goes. Let f be a function defined by f of y equals 1 over the norm of y minus x, like we have stated in this problem. So f is a function that maps from A to R, and it indeed is mapped from A because if you choose any point in A, if you choose any point y in A, then y is not in A complement, so y cannot be equal to x. So the distance between y and x, which is the same as which is the absolute value of y minus x, this must be strictly greater than 0. And so the denominator here is never 0. Okay, so we want to prove that this is unbounded. So to prove that it's unbounded, note that, we need to prove that it's continuous and unbounded. So we'll start with proving unboundedness. Note that X is not in the exterior of a complement because X is in a complement? Right, because the exterior is the interior of the complement. So to say that x is in the exterior of A complement means that x is in the interior of A. But x cannot be in the interior of A, because in order for x to be in the interior of A, it would need to be in A. Right, for x to be in the interior of A, it would in particular need to be in A. But it's not, it's in A complement. Right, because x is in A complement, but not in the interior of A complement. And so, x is in the boundary of A complement, which is also the boundary of A. Right, because you can take the space, given any set A, you can take the space and break it into the interior of A, the boundary of A, and the exterior of A. We've chosen x to be in A complement, so it's not in the interior of A. And it's not in the interior of A complement, meaning it's not in the exterior of A. And so it has to be in the boundary of A. So I think I could have, I guess given that argument, like saying it that way would be less work than what I've done here, but whatever. Okay, so every open neighborhood of x, and by an open neighborhood of x, I really just mean a rectangle containing x. Contains points both in A complement and in A. So in particular, it contains points in A. So given any m greater than 0, what we want to do is we want to find some y such that f of y is greater than m. So we want to choose delta to be a positive number which is less than 1 over m times the square root of n, because A is a subset of Rn. Let U be the direct product of, we take xi minus delta and xi plus delta. So certainly U is an open neighborhood of x, and for any y in U intersected with A, which is non-empty because y is in... No, this is non-empty because U is a neighborhood of x, and x is in the boundary of A. So, just say that. We have... What do we know? We know something. We have the distance between x and y is, so this is just by definition, the sum of, we take xi minus yi squared, then we take the square root of this entire thing. And now the distance between xi and yi must be less than delta, because delta is the radius of each interval at each coordinate. So this is less than or equal to the sum from I equals 1 to n, delta squared, take the square root. And this is precisely equal to, well, let's see here, we're taking delta squared and adding it n times, so we get n times delta squared, and taking the square root gets us the square root of n times delta. So, f of y equals 1 over the norm of y minus x, which is, the denominator is of course exactly equal to the norm of x minus y. And because it's in the denominator, we can, when we know that the distance between x and y is, let's see here. So we know that the norm of x minus y is less than or equal to square square root of n times delta. And so when we do this, it's going to turn the other way because it's in the denominator, so it's going to be 1 over delta times the square root of n. And delta is chosen such that delta is less than 1 over m square root of n. So 1 over delta is going to be greater than m times square root of n. And that'll be in the numerator now. And we're dividing by the square root of n still, and this is just m. Thus, f is unbounded. Because given any positive number m, we can find a point y such that we plug into f and get a number which is greater than m. And as we would expect, basically we get closer and closer. We choose points y which get closer and closer to x, and then f of y will equals 1 over this thing that gets smaller and smaller, and so the fraction itself gets larger and larger. And so it goes to infinity. And so it's unbounded. As for continuity, note that I'm going to go into perhaps more detail than necessary here, as I usually do. Let's define a function n of x to just be the norm of x is continuous from Rn to Rn because for all x in R, for all epsilon greater than 0, if the distance between x and y is less than epsilon, then the distance between nx and ny, well, this is just this, and this is going to be less than or equal to this, and this should be, this is the reverse triangle inequality, and this is less than epsilon. So basically, what we need is that for all x and r, for all epsilon greater than 0, for continuity, we need to find some delta greater than 0, such that if the distance between x and y is less than delta, then the distance between n of x and n of y is less than epsilon. And here, this is sort of the easiest possible scenario, because you can just choose delta to be precisely epsilon, and it works. Okay, so taking the absolute value is a continuous function. Next, and this one's a little trickier, g be a function from non-zero real numbers to real numbers be given by, or defined by g of x is 1 over x. Of course, all the x's that I'm using here are not the same as the x that I fixed at the beginning of this problem to define the function f. These x's I'm just using as variables. To prove g is continuous, given x non-equal to 0, so that's in the domain of g, and given epsilon greater than 0, we need to choose delta greater than 0 such that, and this is really weird, and this took me a bit to come up with, and when I write this, it's going to be completely like, where did I possibly get this? And as is usually the case in exercise, in proofs where it's like, where did you get that? You get it by working backwards. So delta needs to be less than epsilon times the norm of x squared over 1 plus epsilon times the norm of x. this guarantees, so why do we do this? So now we'll do a little bit of work. We just do some algebraic manipulation. So delta times 1, we basically take the denominator and multiply it over. Obviously it's a positive number, so we don't change the sign when we do that. And this guarantees, so this, and this implies, let's see here, if we multiply this out, we'll get delta, and then we'll get delta times epsilon times the norm of x, which we move to the other side. So we'll have epsilon times the norm of x squared minus delta epsilon norm of x. And then it guarantees that delta is less than epsilon times x, here we just factored things out, times x minus delta, norm of x minus delta. Okay, and this is what we need to use. And so basically when I was doing the calculation, I'm like, what does delta need to satisfy? And delta needs to satisfy this inequality that we ended up with. And so then I worked backwards and solved for x. To prove that this works, so suppose that the norm of x minus y is less than delta, then delta is greater than norm of x minus y, obviously, which is greater than or equal to the norm of x minus the norm of y. This is just, you first do the reverse triangle inequality, and then you remove the absolute value signs on the very outside, because that can only decrease what you get. So, what does this tell us? This tells us that norm of x, we sort of move things around. We move the norm of, what do we do here? We take x and we move the delta over to this side, and that's going to be less than the norm of y. And thus, what we have is we take 1 over x, so perhaps I should say g of x minus g of y, which is 1 over x minus 1 over y. Well, let's see here. So we want to combine these two fractions, so this becomes the numerator, let's see here, we get y over x times y minus x over x times y. And if you take the absolute value of that fraction, that's the same as taking the absolute value of the numerator and the absolute value of the denominator. So we get the absolute value of x minus y on top, and on the bottom we get the absolute value of x, y. And the distance between x and y, oh no, do I have an inequality in the wrong direction? No, okay, thank God, okay. So this is, so the distance between x and y is less than delta. And on the bottom, we have x, y. And what did we prove earlier? We proved that delta is less than epsilon times the norm of x squared. No, we proved that delta is less than epsilon times the norm of x times the quantity norm of x minus delta. So this is going to be less than epsilon times the norm of x times the norm of x minus delta, and then we divide by the norm of x times the norm of y. And so we can cancel out the norm of x, and we know that the norm of x minus delta is less than y. And so this is going to be less than epsilon times the norm of y divided by the norm of y. But that's precisely epsilon. So this is how we came up with this weird formula for delta. What I ended up with was I started with, okay, so we get, I took the absolute value of 1 over x minus 1 over y, and I got to this norm of x minus y over the norm of xy. And I knew that I needed this thing to be less than epsilon. And see here. So that means that you need epsilon times the norm of x times y to be greater than the norm of x minus y. And I think I just like manipulated that algebraically a little bit and got to this identity delta is less than epsilon times the norm of x. No, delta is less than epsilon times the norm of x times the quantity norm of x minus delta. And then I sort of work backwards from that and solve for like what I just solved for delta there. Okay, so that's how you find delta. And it's what you need to choose in order to get this. I saw some different proofs online, but I sort of like this one because it's just straight analysis. All right. So, G is continuous at x, or rather, so G is a continuous function on its domain because it's continuous at every point x in its domain. All right, so lastly, theorem 1-8 allows us to prove that, and I'm surprised they didn't state this as a corollary, compositions of continuous functions are continuous. And why is that? Well, theorem 1-8 tells us that an equivalent definition of being a continuous function is that the inverse image of any open set in the codomain is an open set in the domain. So the way this works is that if you have a function, let's just say you have f of g here. If f goes from a to b and g goes from b to c, then if u in c is open, if we take f of g, no, this would be g of f inverse of c. So g of f means first you apply f and then you apply g. So if you take the inverse of g of f, first you pull it back through g and then you pull it back through f. So g of f inverse of c is you take f inverse of g inverse of c, okay, so of course we're assuming that f and g are continuous functions. So if you take the inverse image under f of g, the inverse image under g of f of the open set C, well, first you pull it back through g, and then you get an open set in B. So g inverse of C is open in B because g is continuous. And so then you have an open set with B, and you're taking its inverse image under f, where f is a continuous function. So you'll end up with an open set in A. So f inverse of g inverse of c is an open set in A. And so the inverse image of any open set under G composed with F is an open set, and so G composed with F is continuous. So therefore, compositions of continuous functions are continuous. So what does that tell us? Well, our function f is 1 over, so f of y is 1 over the norm of x minus y. And the norm of x minus y... Oh. I'm missing one. If h of x... No. H of y equals x minus y, then, let's see here, f of y equals 1 over the norm of, I know it's x minus y minus x, doesn't matter. So h of y is a continuous function, and you can prove that if you want. I won't prove it here because this is just a linear function. Because h of y equals x minus y, x is a constant term and y is the linear term, so it's just a line with slope minus y, and so it's going to be continuous. You can use a delta epsilon argument if you want, and I think delta would just depend on epsilon and on the slope of this line, which is minus y. And so you can work through the details if you want, but it should work out really nicely. So anyways, so this is 1 over the absolute value of h of y. And this is 1 over n of h of y. So this is, what did I call it? G? G of n of h of y. So f equals g composed with n composed with h is continuous because each of these three functions that we've chosen are continuous. And let's see here, I guess the only other thing with continuity is that you sometimes have to worry about the domains of the functions. But really the only thing that we would have to worry about here would be the function g, because the functions n and h are defined. H is defined from r to r, and n is defined from... Wait. N doesn't go to Rn. N goes to R. So an h of y should go from Rn to Rn. Oh, so I guess that for the continuity of h, delta would potentially also need to depend on the dimension of the space n. So you might have to use like a square root of n like we do in all of these arguments where we're dealing with open rectangles in Rn. But anyways, h is defined from Rn to Rn, so it's fine. N is defined from Rn to Rn, so it's fine. G is defined from all sets, or all non-zero real numbers to R. So the only real potential issue would be with the domain of G, but that's not really an issue because G is continuous, or because... Yeah, because G is continuous. Really, the only place where that can be an issue is if the domain of one function and the codomain of one of the other functions don't quite match up. So, like, if we were composing, if we had, like, let's say this function were, like... Let's see here, f, g, h, I. No, that's not a function. Let's call it f tilde. So let's say we had f equals f tilde of g, of n, of h. And if f tilde was a function from r to r, then there might be some potential issues because the codomain of f tilde would be all of R, whereas the domain of G would just be all non-zero real numbers. So there could be some potential issues there. But In this case, it's fine. We have f is a composition of continuous functions, so it's continuous, and we prove that it's bounded, and those are the things that we wanted to prove, and so we're done.